Previously, we have talked about single-qubit gate. Now let us look at multi-qubit gates. We will start with a two-qubit gate. For example, here I have drawn a circuit representation of a two-qubit gate that the input states are initialized in the product state 0, 0, and each of them is subject to a unitary operation. The output is hence U1 tensor with U2 acting on the input state 0 tensor 0. It is quite straightforward to see that no matter how arbitrary this two unitary is, the action of this two unitary state acting on this input state, which we initialize as a product state, cannot give us an arbitrary two-qubit state. This is because this is simply U1 acting on 0 tensor with U2 acting on 0, and that output state remains a product state. It is a separable state, however we know that many two-qubit states are actually entangled. For example, the famous Bell states are the maximally entangled two-qubit states. In order to produce an entangled state, we need a two-qubit gate that is not of the form of a tensor structure of two unitaries U1 and U2. And such gates are called entangling gates. In the case of two-qubit, the prototype of an entangling gate is the so-called controlled NOT gate. This kind of gate are called controlled operations, and basically controlled operations are simply conditional statement. For example, if A is true, then do certain task. Here, I've shown the circuit representation of the controlled NOT gate, which is also called the CNOT gate. What it does is that for these two input states, one of them is labeled as C, which stands for control, while the other one is labeled as T, which stands for the target. The control is always left unchanged, so if it's 0, it goes out as 0. If it is 1, it goes out as 1. However, for the target, as you can see, what happens is that if the control is in the 0 state, the target comes out unchanged. However, if the control is in the 1 state, then here the target state is flipped from 0, 1 and 1 to 0. So mathematically, we write T addition C modulo 2, where this additional modulo 2 means 1 plus 1 is equal to 0. So if nothing is specified, we normally assume that the top line or the top wire is the control qubit. So with the dot over here, so that controls what we do on the target qubit. So here, what we will do is that if C is equal to 0, nothing happens to the target state. If C is equal to 1, then we do an addition modulo 2 to the target state, with the additional modulo 2 between the T and the C. In terms of the basis, what the CNOT gate does is effectively turning the basis cat 0, 0 remains as 0, 0, 0, 1 remains as 0, 1. So the first qubit is the control and the second qubit is the target. So if the control is in 0, nothing happens to the target. However, if the control is in the 1 state, then the target state is flipped from 0 to 1. So this basis cat 1, 0 turns into 1, 1, and the basis cat 1, 1 turns into 1, 0. So as you can see, the target is flipped if the control is in the 1, otherwise it remains unchanged, but the C always remains the same. As you can see from this basis transformation, this is a basis and this is another basis. So what it does is only flip this two basis cat. So that means the CNOT is a unitary because it transforms between two different bases. So the matrix representation for CNOT in the computational basis is simply 1, 1, 0 elsewhere. However, flipping this 2. So that means you have 1 and 1 over here and the rest are 0. I will leave to you to verify that this CNOT gate is a unitary operation in a sense that the CNOT times the CNOT emission adjoint is the identity operator. Now, let us see how the CNOT gate creates entangled state. So here I have a circuit for producing entangled state where the initial state is in the 0, 0 state, and a Hadamard gate is applied on the first qubit, the control qubit, which turns it into a superposition of the 0-1 state. At the CNOT, what we see is that the first part of the combined system, which is 0-0, remains unchanged. However, the second part, 0-1, because the control is in the 1 state, so it flips the qubit from 0 to 1 for the target. So we will have 0-0 and 1-1. And this is the one of the Bell state, the phi plus state. How to produce the other 3 Bell states? Well, that is why I've drawn a box with the U inside, where the U could be certain unitary that help us to produce the other 4 Bell states. So if the U here is the identity, then the output state will be the phi plus. How to produce other Bell states? Well, if I apply a X operator on the target state after the CNOT, what you will see is that the X flips the 0 and 1 for the target state, so then we will have 0, 1 here and 1, 0. And that gives us the other Bell state, which is the psi plus. If I would like to produce the phi minus, which is 0, 0 minus 1, 1, I need to add a phase of minus 1 in front of this cat. So for that, I can apply a Z gate. That adds a phase of minus 1 to this part. So then I will be able to produce 0, 0 minus 1, 1, which is the phi minus state. So as an exercise, you could work out what is the unitary needed in order to produce the psi minus state. You might have already realized the CNOT gate is in fact very similar to the XOR gate in classical computing. So in classical computing, we have many 2-bit gates, for example, the NAND gate, the OR gate, and here I have drawn the picture for the XOR gate with the truth table shown over here. The XOR gate takes 2 inputs, X and Y, either 0 or 1 as a bit, and produces the output, which is Y addition X modulo 2. So that's exactly the same as what happens here for the controlled NOT gate. If both of the inputs are 0 or both are 1, then the output is 0. However, if one of them is 0 and the other one is 1, then the output is 1. So this 0, 1, 1, 0 is exactly as we can see for the output for the target qubit 0, 1, 1, 0 over here. The CNOT gate can also help us to evaluate certain types of functions. So for simplicity, let's consider this example where the function is defined only on the input being either 0 or 1, so it's a bit, and the output is also either 0 or 1. There are altogether 4 such functions that are possible. The first one is that the function is always equals to 0, the output is always 0, doesn't matter whether the input is x or 1. The second type is that the function is always equal to 1. Again, doesn't matter what is the input. So this kind of functions are called constant functions because the output is just a constant value. There is the third type where the f of x is equal to the x. So if the input is 0, then the output is 0. If the input is 1, then the output is also 1. And the last type is switching the input. So when the x is 0, the output is 1. When the input is 1, then the output is 0. So that is mathematically expressed as x plus 1 modulo 2. And these two are called balanced functions. They have different output depending on the different inputs. The CNOT gate can be used to evaluate the function of the balanced type. Let's find out how. So looking at this circuit, first, let me assume that the y is initialized in the 0 state, so the target is put as 0. Then, after going through the circuit, we have y plus the f of x for the CNOT gate if the u is the identity. So here, simply the output will then be, so for this type, for the evaluation of the function f of x equals to x, so what we need is to set the unitary equal to the identity. And as you can see, the output over here, the y is 0. So then the f of x is equal to x. So the output will be x over here. And finally, in order to evaluate the function of this fourth type, what we will have for the u is to set it as the x gate, which flip the state of the target qubit one more time, and hence the x is turned into x plus 1 modulo 2. Hence, we can see that the CNOT gate can be used to evaluate the function of the balance type for this particular function. We can also use the CNOT gate to make copies of orthogonal states. So for example, here I've shown the input state as a superposition of A0 plus B1, and the target state is set to be 0. So this is the state to be copied, and this is thought of as our blank paper. At the output, we have the state A00 plus B11. As we can see here, unless one of the term is 0, so for example, if A is equals to 1 and B is equal to 0, or B is equals to 1 and A equals to 0, then we are making a copy of the state 0 or 1. But in general, this is not true for an arbitrary state A0 plus B1. So we can only make copies of orthogonal states in quantum computation, not for an arbitrary state. This theorem is known as the no-cloning theorem, that it is impossible to make a copy of an unknown generic quantum state, and you will learn more of this in the introductory course to quantum information. Besides the CNOT gate, there are also other types of controlled gate. Actually, the CNOT gate is also called the controlled X gate, and sometimes in the circuit representation, you could see this addition modulo 2 being replaced by a box with the X inside. And they are doing exactly the same thing. So there's another type of controlled gate called the controlled Z gate, which adds a phase of -1 if the input is 1, 1. Otherwise, the other three states are all unchanged. The matrix representation in the computational basis is hence with 1s on the diagonal elements for the first 3 diagonal entries and with a -1 on the last diagonal entry. We can also convince ourselves that it is possible to build the CNOT gate from the controlled Z gate. In fact, by adding a Hadamard on the left and the right together with the controlled Z gate, it is equivalent as the controlled X gate or the CNOT gate. In fact, the controlled NOT gate and the controlled Z gate are just special case of a general controlled unitary gate. So here I have replaced this by a box with a general unitary inside. So the state transformation goes from the control target to control unitary to the power C acting on the target. If the control is in the 0 state, so this will be the identity, nothing happens to the target. If the control is in the state 1, we apply a general unitary on the target state. Some special cases are what we have already seen. There is also the controlled phase gate, that is to replace the unitary by the phase gate we have studied before. The action of that controlled phase gate is to turn the state 1, 1 into I, 1, 1, adding a phase of I in front of the state 1, 1, while leaving all the other 3 basis states unchanged. Finally, to conclude the study of 2-qubit gates, there is one more non-trivial gate called the swap gate, which swaps the state of the first qubit with the second qubit. So if the state is in 0, 0, nothing happens. If the state is in 1, 1, also nothing happens. However, the state 0, 1 is swapped to 1, 0, and the state 1, 0 is swapped to 0, 1. The circuit representation of the swap gate is shown like this, with 2 cross on the 2 qubits. Its matrix representation in the computational basis is shown in this way. As you can convince yourself, since the state 0, 0, and 1, 1 are unchanged, so we have the diagonal entry of 1 and 1 over here. For this blocked part, because the swap gate changes these 2 bases, so we have off-diagonal elements 1 and 1 over here. In fact, the swap gate can also be composed from the CNOT gate. So the swap gate is equivalent to 3 CNOT gate. However, here you should note that in the second CNOT gate, the role of the control and the target are interchanged. So rather than the first line being the control, now the first line is the target for the second CNOT, whereas the second line is the control qubit. As an exercise, you can verify that they are indeed the same, perhaps by using the matrix representation of the swap gate and the matrix representation for the CNOT gate. So we have already talked about the matrix representation for the CNOT gate, where the first line is the control. How about the matrix representation for the CNOT gate, where the role of the target and control are interchanged? So for that, we note what will happen is the basis transformation is the 0, 0 goes to 0, 0. The 0, 1, now remembering the second one is the control, so the target will be flipped. 1, 0 remains as 1, 0. And the 1, 1 will become 0, 1. As an exercise, from the basis transformation, you should be able to work out the matrix representation of this gate in a computational basis, and then you can verify that these two gates are equivalent. To conclude the discussion on the single qubit and two-qubit gates, there is a reason that we study them in quite some details. This is because the single qubit and CNOT gates are universal. Here, let me explain the meaning of the word universality. In classical computing, a set of gates is said to be universal if any arbitrary classical function can be computed using this set of gates. For example, we know that in classical computing, the NAND gate is a universal gate. That is to say that using only the NAND gate, we can compute the value of any arbitrary function. There is a similar statement for quantum computation, which is written down over here. Hence, in order to carry out a general quantum computation task that could act on any qubit, it is sufficient to be able to realize only the single qubit and the CNOT gate. And let's remember that the single qubit gate, which are those general unitaries, can be decomposed in certain axes, so it is again not necessary to carry out the general unitary around an arbitrary direction. In fact, we only have to be able to realize those unitaries around specific directions. So there is even another simplification of this statement, that is, using only the set of Hadamard gate, phase gate, the T gate, and the CNOT gate, this set of 4 gates are said to be universal, because using only these 4 gates, we can actually realize any general unitary up to any arbitrary precision. While the proof of this goes beyond the scope of this course, we will refer you to some references at the end of this lecture. Here, rather than showing the proof, let me just show you another demonstration. For example, in the case of 3 qubits, there is a famous state called the GHZ state. Let me write it down. So this state is an entangled state and is said to exhibit genuine multipartite entanglement. As you can see here, if the first qubit is 0, the second and third qubit must also be 0. And so if the first qubit is in 1, the second and third qubit are also in 1. This is similar to the Bell state, but here it's a genuine multipartite entangled state. To create this state, it seems we need a gate that entangles the 3 qubits as a whole. However, it is actually possible to generate this state using just CNOT gate and single qubit gate. The circuit goes like this. So here we will initialize the state as a product state of 0, 0, 0, and apply a Hadamard on the first qubit. After that, we apply 2 CNOT gate. The first CNOT is applied between the first and second qubit, and the second CNOT is applied on the first and the third qubit. So you can easily verify that at the end of the first Hadamard, the state goes to 1 over square of 2, 0 plus 1. And the action of the first CNOT together with the action of the second CNOT, both are 2-qubit CNOT gates, will eventually produce this state. Let me also introduce you to a 3-qubit gate, which is called the Toffoli gate, that you will see in more advanced course in quantum computation and quantum information. This Toffoli gate in passing is just a controlled CNOT gate. So there are 3 input, A, B, C. The first two act as the control, both A and B, whereas the C is the target. What the Toffoli gate does is that it flips the target qubit only when the first two control qubits are both 1. In terms of action on the basis cats, when the cat is 110, it will be turned into 111. When the state is 111, it's being turned into 110. So only when the first two control are both 1, the state of the target is flipped. While for the other 6 basis cats, they will remain unchanged. This gate is important because the Toffoli gate can be used to simulate the classical NAND gate. And we know that the NAND gate is universal for classical computation. Hence, using the Toffoli gate, we can simulate any classical function on a quantum circuit. Finally, let me remark that we've already said that single qubit and CNOT gates are universal, so it is possible to decompose the Toffoli gate as a sequence of single qubit gates and CNOT gates. This also goes beyond the scope of this course, and you will learn them more in more advanced courses.